question here is, which process is endothermic? And this goes all the way back to the beginning of chapter 8, where we looked at processes and labeled them as endothermic or exothermic. I'll prove to you which slide I'm talking about. The very beginning of chapter 8. Maybe I can just, right here. Okay, remember, yeah, that figure right there, where we talked about transitions between solids, liquids, and gases. And we labeled each kind as endothermic or exothermic. So anything that's going from a solid to a liquid or liquid to a gas, so anything with an upward arrow, that's endothermic. To become more gas-like, to melt or to vaporize, you have to absorb heat, okay? Think about ice. Ice has to absorb heat to melt. Liquid water has to absorb heat to boil or vaporize, okay? So because anything that's absorbing heat, we said down here, is endothermic, positive delta H. Anything releasing heat, because it's going from a gas to a liquid or a liquid to solid, any of the downward arrows, has that little blue phrase by it saying heat released. That's exothermic, negative delta H, okay? So we made a note of that. So anyways, that was what this first question on the exam was getting at. And you can see that A is going from a solid to a gas. So that is definitely a positive delta H. B, you're going from a liquid to a solid, so that's like freezing. So that would be releasing heat. So that would be a negative delta H. So that's not what we want. And that's what we're asking for here. C is a liquid to a gas, so that would have to absorb heat as well. So you got 2 here, A and C, which means you needed to select F. That's lagging. Okay. That was the first one, was F. 2, which of the following molecules can hydrogen bond in pure form, meaning no water molecules around, just identical molecules like themselves. So you're looking for something, a molecule that has a donor plus an acceptor in the same molecule. Okay, so it needs to have a positively polarized hydrogen, which is a hydrogen bonded to an oxygen or a nitrogen or a fluorine. Okay, so we're looking for that. And then the acceptor is a lone pair on an oxygen, a lone pair on a nitrogen, or a lone pair on a fluorine. So I gotta have both things. So obviously B can't be it because we don't even have an oxygen, nitrogen, or fluorine. C can't be it because we don't have hydrogen or oxygen, nitrogen, fluorine. D can't be it, same reasons. So I'm just gonna look at A and E. So again, hopefully there's ways where you can quickly minimize your answer choices. Now this would be the way I would do it. So A, here's what I noticed. If you want to draw it out, I got CH3, and then I got an O and an H. So definitely I got the acceptor there. And this is a hydrogen bonded to an oxygen, so that's positively polarized. So this one should be our answer. Let's check E though, because I have another hydrogen bonded to a carbon, triple bonded to this nitrogen. I do have the lone pair on a nitrogen, but this hydrogen is not a donor, okay? It's not positively polarized because it's not bonded to oxygen, nitrogen, or fluorine. Sorry, this is so slow. Okay, so it's not E. A is our answer there. All right. Goodness gracious. Number 3, put the following molecules in order of decreasing boiling point. So start with the highest and with the lowest. All these molecules are nonpolar. So what kind of intermolecular forces would they have? Line dispersion. Yep. And what did we say about line dispersion forces? Yep, the bigger the surface area. Okay, so larger atoms have more electrons, more fluctuation, more London dispersion forces. Last bullet point there, molecules with larger surface area will also have more London dispersion forces. And here's an example. Okay, when it's more elongated, there at the bottom pentane, higher boiling point than this 2,2-dimethyl propane. So we emphasize that. So the more surface area something has, the bigger something is, the more London dispersion forces it can have, and the higher its boiling point would be. So we just need to pick the largest and go to the smallest. So 3 there is our largest, 1 is our smallest. So it should be 3, 2, 1. So that's D. Some people picked A. Maybe they just got it backwards. So FAD, page 1. Number 4, which of the following reactions has a negative change in entropy? So I'm looking for a negative delta S, meaning you're decreasing in disorder, or you could say it as you're becoming more ordered. So in which reaction are we becoming more ordered? So A, I see that I've got something that is aqueous plus 2 moles of another thing that's aqueous. On the product side, I have, again, 3 moles of things that are aqueous, 2 reactants, 2 products. So nothing there should scream that it's becoming more disordered. It's the same on both sides. You got 2 reactants, 2 products. Everything is aqueous. You're not changing from a gas to a liquid or solid or anything. And you have the same number of moles. You have 3 moles of stuff on both sides. So A is not increasing or decreasing. Okay, B, you have 6 moles of gas, okay, because there's an understood 1 right here. Plus 5 more makes 6 moles of gas on the reactant side. On the product side, you've got a 3 and a 4. That's 7 moles of gas. So you're making more moles of stuff. So that's more disordered. So again, this one, or sorry, B has a positive delta S. C, I have solid and gas come together and make something that's just solid. I have 7 moles of stuff. If you look at the 4 and the 3, and now on the product side, I just have 2. So this is way more ordered. Okay, when you just have a solid, and you did have a solid and a gas. So this is definitely a negative delta S. So C was your correct answer there. Okay, 5, I think some people struggled with 5, maybe. It says for the reaction, how much energy would be absorbed when 10 grams of ammonium chloride is dissolved in water? So which one's ammonium chloride? Yeah, this one right here. So I give you the delta H, and we're starting with 10 grams of the NH4Cl. Well, I know if I look at the reaction here, that for every 1 mole, okay, it's units of moles, for every 1 mole of ammonium chloride, I'm going to get, or I have to absorb 15.1 kilojoules of energy. So that's a relationship, okay? 1 mole of NH4Cl is related to the reaction absorbing 15.1 kilojoules of energy. So if I could just convert this grams, 10 grams to moles, then I could directly convert to kilojoules. So lots of problems like this directly on your homework. That octane problem on the homework, where you had to, there's like parts A, B, C, D, and E on that problem. I got lots of questions about that problem. That was just like this stuff, converting between grams and moles and ultimately to kilojoules or vice versa. So we need the molar mass of that, which is going to be 14.007, 4.032, and chloride is like 35.4, we'll say. So again, you add it all up, 39, 49, 50, it's like 53.4, we'll say 39. It probably wasn't this exactly, but very close, okay? Gram per mole. So then you would divide by 53 point, we'll say 439. I'm probably off by just a little bit on this for 1 mole. And so the grams cancel. And this is ammonium chloride, NH4Cl. So now I'm going to plug in this relationship for every 1 mole of NH4Cl. So that moles cancel. We absorb 15.1 kilojoules. So you'll do 10 divided by 53. And I don't have my calculator on me. Times 15. 10 divided by 53. And I got 2.82. Okay, so C was the correct answer there. Kilojoules. So that was a little bit of work. for that one. All right, 6 is just how much do you know about the word exergonic? What does it mean? So an exergonic reaction, the slide that I pulled this from was right here. Okay, this is where we talked about and defined what exergonic is and means. Okay, so you can see delta G is negative, the reaction is spontaneous, products are lower in energy, more stable than reactants. So let's just go back and see the questions asking for which says an exergonic reaction. So A is true, has a negative delta G. Is reaction where the products are more stable. Yep, that's true. Lower in energy than the reactants. Is favored by a negative delta H and a positive delta S. That is true if you go look at the table. Is always spontaneous. Yep. So E, all are correct. Any questions so far on these? Like why? Maybe why something went wrong if it did. Number 3. D. Yeah, 3, 2, 1. All right, number 7, at constant temperature. Whoa, that should tip you off right there. Constant temperature. So this is combined gas law. We're going to pull temperature out. It says a balloon contains 2.5 liters. That's a volume, so that's my V1. At a pressure of 17.6 psi, that's my P1. What would the volume be? So I'm looking for V2. If the pressure was 5.75 psi, that's P2. And my units for psi are the same, so I don't have to convert here. So it's P1 V1 over T1 equals P2 V2 over T2. And we're just going to remove the bottom part because temperature is going to be held constant. So P1 V1 equals P2 V2. I'm solving for V2, so I'm going to cross divide both sides by P2. Cancels there. So I'm going to plug in P1 and V1 on the top. So there's my P1 V1. This is liters, 5.2, or sorry, 2.5 liters times 17.6 psi. Divide that by P2, which is 5.75 psi. That's going to be V2. So 2.5 times 17.6 divided by 5.75. You should get 7.39. Did I type something in wrong? Maybe I typed something in wrong. I think it's a 7.65. 2.5 times 17.6 divided by 5.75. There. Sorry, I must have hit a wrong number. Okay, 7.65 liters. So B was the right answer there. All right. Next one. Okay, this was right out of your lab. Says you're doing an experiment in lab with the following chemical reaction. Same reaction from our Le Chatelier's lab. The experiment that turned like blue and pink and purple. Did the hot bath and the cold bath. So there's the reaction with the cobalt chloride and the water. Makes that cobalt, hydrated cobalt and the chlorides. Says the reactant, COCl4 with a -2 charge, is dark blue in color, while the product, the cobalt with the waters, is pink. You add ammonium chloride to your test tube. You notice the color changes from pink to dark purple. Which of the following statements is true regarding your observations? So, by the way, just real quick, ammonium chloride, which we had a problem on this earlier. So it's NH4Cl. In solution, what's it going to break up into? What ions? NH, ammonium, NH4 plus, and chloride. Okay, so these ions are what we're going to have in the test tube with our reaction. So your options are which one is a spectator ion and which one can affect or increase the concentration or shift equilibrium. So the only thing that can shift equilibrium is anything that's in this reaction. So let's look at ammonium first, NH4. Do I have ammonium anywhere in this entire reaction? Nope, it's not a product, it's not a reactant, it's not involved with anything. Okay, chloride ions. Do I have those anywhere in my reaction? Yes, I do. They're right here. They're a product. Okay. So we got to find the one where it says ammonium is a spectator ion. Chloride can shift equilibrium. And if you increase the concentration of a product, you saw it turn from pink to blue. Okay, because you can label it. This one was pink. Product side was pink. Reactant side was blue. So it's shifting left. So you automatically should have crossed off anything that said it's shifting right. That's not correct. So you're just picking between A and B here. And B is the one that says ammonium is a spectator ion. Chloride ion, an increase in that would shift equilibrium left. Okay, so B is the correct answer there. It's so slow. Sorry, guys. There. All right, number 9. Which of the following statements is true? For any given substance, heat of fusion will always be larger than heat of vaporization. That you honestly should just go look at the table at the end. I gave you this table. If you look at all the heat of vaporization numbers compared to heat of fusion numbers, every single one of them is bigger. Okay, it takes way more heat or energy to take something from a liquid to a gas phase than it takes for something to melt solid to liquid phase. Okay. So what I mean is that, the numbers over here on the right are always bigger for every substance than the numbers in that column on the left. Okay, so heat of vaporization is always larger. So that is not true. Heat of fusion will not be larger. So A is not true. Okay, B, decreasing the temperature of a reaction will increase the reaction rate. What do y'all think about that? Yeah, false. You got to increase the temperature to increase the reaction rate. Okay, C, for a gas, pressure and volume are proportional. Pressure increases, volume also increases. I try to set you guys up. I promise I try to set you guys up for success if you answer your previous questions correctly. We just worked a Boyle's Law problem, number 7. And what did we find? Okay, as pressure decreased, volume went from 2.5 to 7.5 almost, right above. So as pressure decreased, volume increased. Okay, because they're inversely proportional. If one goes up, the other variable goes down. Oops.
Is there something that the pressure and the volume are proportional for? I picked C and I was very confident.
No, pressure and volume are never directly proportional. Pressure and temperature are proportional. Volume and temperature are proportional, but pressure and volume are inversely proportional. In the gas laws, like in the slides, I made sure to have you guys specifically write those things down. So when we were doing the Charles Boyle's Gay-Lussac's law, remember these statements at the bottom of every slide? We would write these out. Inversely proportional, pressure and volume. Now temperature and volume are proportional. Temperature and pressure, those are also proportional. One increases, the other increases. But pressure and volume are inversely proportional. And hopefully you proved it to yourself on that Boyle's Law problem. I forget on the earlier multiple choice. So A is not correct. B is not correct. C is not correct. D, a catalyst can increase a reaction rate by lowering the activation energy. That is absolutely true. D. And we even drew reaction diagrams with and without a catalyst in lecture. Last one, number 10, which of the following molecules? I actually accepted 3 answers here. Which of the following molecules cannot hydrogen bond but can interact via dipole-dipole interactions? Now here's the deal. I did not say in pure form, and I should have, because in my head I was intending it for it to be in pure form. So I think what a lot of people did is they saw SO2. And they were like, oh, this has lone pairs on the oxygen, so that could hydrogen bond with water. And it could with water, but not with itself. But if you look at sorry, we're saying which one cannot hydrogen bond, but can interact via dipole-dipole interactions. But because I didn't say in pure form, that's where I was like, well, maybe some people thought, hold on, but I want to look at the electronegativity chart too, because you need to take this into account when you are when you're drawing this out. So we had O and S. The difference there is 1 in their electronegativity values. So sorry, I need to find that problem again. Okay, right here. Some people too, though, may remember that this molecule is bent. And so you would draw these pointing outwards like this. But some people, because there was a slide, what chapter was that? When we introduced molecular geometry, but all the way back in chapter 4, when we learned molecular geometry, SO2 was an example molecule. And you may not even have remembered this, but some people did. And that sulfur had a lone pair. And so I actually, if you gave me answer choice A, because it's bent, I accepted that as it could have dipole interactions. Okay. Again, it all goes back to the geometry. So I accepted A. B obviously is not a molecule that this can hydrogen bond. Okay, because this OH group right here, you got donor and acceptor right there, so that can hydrogen bond. So you should not have picked B. If you pick B, I counted you wrong. If you pick C, I counted you wrong, because that's a nonpolar molecule. So no dipole interactions, no hydrogen bonding. If you pick D, this one is polar. See, sorry, I meant to draw it out. Like this, okay? So you got this dipole pointing towards the oxygens. So D was the original correct answer that I intended. And then some people might have picked E as well, because some people, again, may have been thinking, anyways, I accepted A, D, and E on this one, which was crazy. I intended for D to be the only right answer, but the more I thought about it, and some people, based on what they drew out and what they explained to me on their paper, or what they drew, if you picked A, D, or E, I accepted all those as right answers. Okay, so I'll circle through. All right, now it gets to the hard part, right? These were all the file response, or not file response, open response. I wanted to see your work. I want to see units. So this one, here I'm asking about considering table 8.5, which is at the end of the exam, explain in 2 to 3 sentences why in their pure form, molecules like ammonia or water have higher heats of fusion, higher heats of vaporization compared to molecules such as butane or ether. You can draw pictures, but that's optional. Okay, so this all goes back to the very end of chapter 8, right here. We discussed the graph on the previous slide. So right here, we introduced what heat of fusion and heat of vaporization is. And then we looked at the table on the next slide and we said, okay, why do and I asked this question at the very end of lecture when we finished chapter 8. So some of you may have been checked out, but this is where this question came from. And if you'll read down here, it says the stronger the intermolecular forces, the higher the melting and boiling points, which means the larger the heat of vaporization and fusion. So it all has to do with intermolecular forces. What kind? So you need to ask yourself, what kind of intermolecular forces can these molecules have? Whoops. So ammonia and water, what can those do? Hydrogen bonds. Okay. And a lot of people said that on their answer. These can hydrogen bond. But if you just said these can hydrogen bond, I didn't give you the full points. Because I said, why is it higher than butane? So you needed to also assess butane and ether. Okay, so C4H10, these are all hydrogen bonds, okay? And so you see in this whole molecule, it's just carbon hydrogen. This is a nonpolar molecule. So this has London dispersion or van der Waals. And these are the weakest kind. So it's therefore going to have a lower heat of vaporization fusion. And same for ether. Well, ether actually can interact with dipole interactions because this oxygen here is going to be bent. It's going to bend the whole molecule. Like this. So some people drew this out and they drew these dipoles which don't cancel. Okay. And they said, oh, this one can have dipole-dipole interactions. Okay. And both of these are weaker than hydrogen bonding. So I needed you to tell me both kinds. If you only told me these can hydrogen bond, but you didn't tell me the other kind have these intermolecular forces and those are weaker, then I counted off a few points. Okay. And if you didn't assess intermolecular interactions at all, you didn't get any points for this problem. Even if you drew great pictures, you needed to assess why heats of vaporization and fusion are higher. All right, this one, I wanted you to draw a reaction diagram, and I wanted you to draw an endergonic reaction diagram on the left, exergonic on the right. Then I wanted you to label everything, label your reactants and products, label your activation energy and your delta G. So endergonic and exergonic. So endergonic, the products have more energy than the reactants. So every reaction has this energy peak. And in an endergonic reaction, the products, which are here, the reactants are here, the products are going to have more energy than the reactants. So you needed to just make sure that wherever your product level finished, it was higher than where your reactant level started. Okay, it didn't have to look exactly like this, but it had to look similar to this. Okay, then labeling, the activation energy goes from the peak to the reactant energy level. So I need to see a line measuring that distance, and you label that activation energy. Then the delta G was the difference between your reactants and your products. So I need to see this distance labeled as delta G. Okay, so that's a positive delta G. You're increasing in energy as you go from reactants to products. So the reaction's absorbing energy overall. Exergonic is the opposite. You have reactants and then your products finish lower than your reactants. So there's R and there's P. Again, the difference from the reactants to the peak is your activation energy. And then the difference between the products and the reactants, this is your delta G, and you can see it decreases as you go along the path. You ultimately end up at a lower spot. So this is a negative delta G. And you didn't have to put negative there. You just had to put the delta G. Okay. Any questions on that? And we drew these out in lecture. Okay, so this wasn't something that I'd ask you to do that you've never done before. Whoop. Okay. 13. So now we're getting into gas laws. Nitrogen is the primary component of the air we breathe here in Conway, Arkansas, where air pressure is 771.14 millimeters mercury, temperature is 9 degrees Celsius. What would be the volume of 250 grams of nitrogen? So let's go through and label. This right here is a pressure. There's P. This is a temperature, T. What would be the volume? So we're looking for V. And this is an amount of gas, so we need to convert grams to moles, which is going to be our N. So you use the ideal gas law, PV equals nRT. That is what we needed here. And because R equals 0.0821 liters times ATM, mole times Kelvin on the bottom, we got to make sure our pressure and our temperature and everything matches these units. So I see that I don't have anything matching. All right, so I got to do a lot of conversions. So I need to convert for pressure. I need to convert millimeters of mercury to ATM. And for temperature, I need to convert degrees Celsius to Kelvin. Okay, so I got to do 1, 2, 3 conversions. Then I can plug everything in. So I need the molar mass of nitrogen. Here's where so many people lost a few points. You take the 250 grams. Nitrogen is N2. Okay, that's why I gave you that little formula right there, N2. So you needed to do, for nitrogen, you need to do 14 point, what is it, 007? Grams times 2. So you should have got 28.014, something right at that, but it should have been 28 gram per 1 mole, okay? And what you should have ended up with was 8.9 moles of nitrogen. So a lot of people ended up with like 17.8 something. And that was double. So again, I only counted off like, I think 3 points total. If you did the conversion wrong and plugged it in and got a wrong answer, I counted off 3 points, but you got the rest of the 7 if you did everything right, everything else. So that's your first conversion. Number 2, millimeters mercury, you take the 771.14. And you should, you had to know this relationship, 760 millimeters mercury for every 1 ATM. And it was like 1.063. Is that right? I think that was, I think that's right. I have the key right here. No, 1.015. 1.05. Okay. Zero 1.5. Okay, and then temperature, so 9 degrees Celsius plus 273.15. Plug everything in. Rearrange your equation to get V by itself. You needed to cross divide both sides by P. So V equals nRT divided by P. So N is our 8.9 moles. R is our 0.0821 liters ATM over moles Kelvin. And T is our 282.15 Kelvin. Divide all of that by 1.015 ATM. Volume should have been 203 liters. There's a decimal on it. I don't remember the decimal. It should have been 203 point something liters. Okay. Okay, questions on that one? We better hurry. A helium balloon contains 3,500 milliliters of helium gas, initially at this temperature, 21 degrees Celsius and 15 PSI. If the volume increases to, so here's what I automatically noticed. I've got 2 volumes. I've got the milliliters and the liters. This is an ideal gas, or this is a combined gas law problem. P1 V1 over T1 equals P2 V2 over T2. All right, so I've got V1 and V2. V1 and the 15 liters is V2. Room temperature 21 degrees Celsius is T1. 15 PSI is P1. Pascals here is P2, and it says what temperature, so we're looking for T2. So I'm trying to solve for T2. So here's where you can flip the whole thing. T1 over P1 V1 equals T2 over P2 V2. Now cross multiply both sides by the P2 V2. Cancels on the right side. So my final equation is P2 V2 T1 over P1 V1. So that's when I plug everything into. All right, now I got some conversions here because I need to convert my temperature, the 21 degrees Celsius. We're just doing an exam review. I know you are bearing a little bit. 0.15 Kelvin, or sorry, is going to be equal to 294.15 Kelvin. And then I'm just going to convert the pascals to PSI. So P2 here is 7330 pascals. And the conversion was this: 101.325 pascals equals 14.7 PSI. Okay. And when you do that, I think that's where you get the 1.063 PSI. Okay, and then lastly, I need to convert my milliliters, my V1. Whoops, I forgot my units. Milliliters, divide by 1,000 for every 1 liter, so it should have been 3.5 liters. All right, now that I've done all these conversions, I just plug it in. So P2 is now the 1.063 PSI times my V2, which is 15 liters, times my P1, which is 294.15 Kelvin, divided by P1 V1, which is the 15 PSI, and P1 is the times the 3.5 liters. You should have got 89 point, it was like 34 or something Kelvin. Really. Any questions? A lot of conversions. A lot of conversions. But that's why I did. We did the review to practice all these things in lab last week. Okay, this was delta G. We got 3 problems left. All right, so delta G, it says calculate delta G for the following reaction at 32 degrees Celsius, and your delta S was 170.04 joules per mole Kelvin. And I give you the delta H right here. So our equation for delta G, anybody remember it? Yep, delta H minus T delta S. All right, so the 2 things you have to do here is convert temperature to Kelvin. So that should have been 305.15 Kelvin. That was your temperature you're going to plug in. And then you kind of convert your delta S to kilojoules. So 170.04 joules per mole Kelvin. We got to convert that to kilojoules. So there is 1,000 joules in 1 kilojoule. So it's going to give you a very small number. It's 0.17004. And that's now your kilojoules per mole Kelvin. Now I can plug everything in. So you don't have to manipulate delta H at all. A lot of people did though. A lot of people took their delta H and converted to joules. Okay, so a common thing that I saw, I want this to be on the recording in case people watch it, is people would take your delta H over here and they'd say, okay, times, they're trying to convert this to joules, and they would say divide by 1,000 kilojoules, one joule on top or something like that. You're supposed to multiply by 1,000 if you're converting the joules from kilojoules. So they would end up with a number that was like 0.087, like this, for their delta H. When really, if you're converting, so that's wrong. If you're converting, you could work it this way, because I didn't actually tell you what to put your units of delta G in. I didn't say calculate delta G with units of kilojoules. So you could give it to me in joules. But it was supposed to be 1 kilojoule on bottom, 1,000 joules on top. So when you do that, you get 87880. Okay, that big of a number. Now the units are joules. And you could plug that in and run with it. But you had to convert it correctly. And a lot of people tried that, just didn't convert it correctly. So delta G equals, I'm just going to plug in my positive 87 kilojoules per mole, minus, I'm gonna put this in parentheses, temperature 305 times my 0.17 per mole Kelvin. All right, now units of Kelvin cancel on the temperature and the delta S. And what you should end up with is, I think it was like positive 36. Let me check the answer key. 35.97. Okay. 35.97. So positive delta G means what? Spontaneous or not spontaneous? At this way, it is not spontaneous. Okay, but if you notice, you have a positive delta H and a positive delta S. And if you remember from the table, we worked some problems like this in lecture, a problem, and we went back and made a note on our table. I said, everybody go back to row 3 on that table with the delta H and deltas, make a note. When you got a positive delta H and positive delta S, this is not spontaneous at low temperatures, but can become spontaneous, meaning a negative delta G, at high temps, at high temperature. Okay, if we increase temperature right here, our 305.15 Kelvin, if we cranked it up to like 500 Kelvin, at that point, the T delta S term, which is negative because of that minus sign out front, would be bigger than our delta H term, and that would make delta G negative overall. Okay, so if you just gave me not spontaneous at low temps, can become spontaneous at high temps, I would give you 3 out of the 4 points. All right, 16 and 17, and then we're done. This is Le Chatelier's principle. Consider the following reaction and predict which way equilibrium would shift by writing either left, right, or no change in each blank in the following descriptions. So in our reaction here, we've got 1 mole of gas on the reactant side, and we've got 2 moles of gas and 2 products on the product side. Okay, so I'm going to make a note of that. We'll come back later. 1 mole of gas and 2 moles of gas. Okay. And we've got a positive delta H, so I'm going to say heat is a reactant. Heat plus this. So increasing the concentration of chlorine, if we increase a product, it's going to shift towards reactant, so it would shift left. If you decrease the concentration of phosphorus pentachloride, which is a reactant here, it's your only reactant. If you decrease that, it's going to shift towards the reactants to replace what we took away. So again, it would shift left. See, if we increase the temperature, we're increasing a reactant because heat is a reactant. So this way it'll shift towards the products. So here it would shift right. If we decrease the pressure, it's always going to shift to the side with more moles of gas. I'm going to say that again. If you decrease the pressure, it will always shift to the side with more moles of gas. And that is a product side. So here you'd say shift right. If we add a catalyst, no change. Not going to change anything. I know I did a problem like this in the review at least, which I did post to Blackboard so everybody could see that. And there were really great practice problems in the textbook too that had you walk through these examples. All right, last problem, we gotta hurry. Consider the following reaction for parts A, B, and C below. Write the expression for the equilibrium constant. Here I just wanted to write K. You don't have any numbers to plug in, so I just wanted you to plug in your chemical formula. So it's products over reactants, and notice magnesium hydroxide here is a solid. So it'd just be the concentration of NaCl squared over the concentration of NaOH squared times the concentration of MgCl2. So that's all I wanted for A. Some people wrote that on part B because they really weren't sure I was asking for A. But if you wrote it even on part B, I gave it to you. Then you're just going to plug in the numbers. So now K is going to be equal to 0.17 molar squared over 0.41 squared times 0.03. And you should have got like 5, it was like 5.3 when you do all that math. Now you had to make sure, since you're multiplying something down here in the denominator, put this in the parentheses if you do it all at once. Okay. Anytime you have a multiplication sign in the denominator, you've got to put it in parentheses in the bottom. And then lastly, since K is greater than 1, you're going to have more products. So I'd say more products at equilibrium, more products than reactants, okay? Or you could say the forward reaction was favored. All right, that's it. I know we got this next class starting in here in like 10 minutes.